Blender 5 is finally here, and it has introduced a lot of new geometry nodes, in particular the volumetric and grid nodes, and some computations that we can do with those. In previous videos, we have explored how to create a scalar field, a vector field, and how we can compute gradients, divergence, curl, etc. We have created a set of arrows to visualize these vector fields, and we have been able to make some nice animations. In this second part of the tutorial, we will use an additional geometry node introduced in Blender 5.0 to advect or to evolve the quantities inside these fields using the simulation nodes. You will be surprised how easy it is to do these simulations and how big is the potential of these new geometry nodes, especially for the visualization of mathematical concepts and as an important tool to create amazing and realistic simulations and animations. So let's begin with the tutorial. Okay, so let us continue with our tutorial on Blender 5. What we will do now is to create a simulation group in which we will use the new geometry node called Advect to evolve some quantities in the scalar and vector fields that we have created in the previous video. So let's start by grouping some of the nodes that we have. In the previous video, we have just created some Gaussian density, Gaussian distributions for the density, and we have visualized them in this way with our volume cube, and we have also created some set of arrows or some glyphs that allow us to visualize properly the scalar field. So with the vector field. So we have the arrows here that are pointing towards the direction of the gradient of our scalar field, which is shown here as a density cloud of the volume that we have. We have created a set of grids and we have allocated these grids. I have made some modifications from the previous video, and I did just some parallel grids because we did this video that I'm showing right now here. So to visualize the evolution of the Gaussians, we have kept only one single Gaussian. So let's start by organizing a bit the nodes. Let's go to the geometry nodes and let's group the things in a logical way so that it will be easier to work with this. We have, as I mentioned, we have created some grids, which are these nodes here, grid for the visualization of the glyphs, and we have created here some arrows based on the curve line, curve circle, and so the cylinders and the cones. So first thing I will do is group this in one single group. For that I will just press Ctrl G and we will create, now we have the group in this way. We will rename this group, we will call it arrows, and now it is more, we have gained some space in our set of group of nodes. We will keep this as it is. Maybe we will remove all these animations that I did for the video. Just right click and clear keyframes. Also, I think I add some animation from the camera. I will just remove all that. We delete keyframes, and here also I will delete these keyframes. Right click and delete the keyframes. Okay, so now we have, this is the camera. Since I did it for a short video on YouTube, I did this vertical layout, but I will change it just to make it again 1920 times 1080, which is the full HD resolution. I will just move the camera a bit to back side so that we can visualize everything. Okay, we have this group. Now we will group everything that is related to these grids that is taking a lot of space. For that, then we will just maybe I will consider also this node, and we will just keep this as an input to our node called meshed points, which is quite logical, that we will have just defined where the points will be, and then we just add the we make them to be points, and then we add the instances on points. So Ctrl G again, and we will have this. Next we will do is to get rid of all these grids, because if you want to visualize intermediate steps here, or if you want to visualize something more continuous, we see that we have maybe to duplicate these grids many times, or we want to make some grids to be in the C plane. This will be very difficult, so I will just show a different way in which we can be sure that we are considering a more continuous set of points in the volume that we have. For that, I will just maybe disconnect this node just with Control right click, and we will build a three-dimensional set of points, a three-dimensional array of points. To do this, then what we will need to do to start is just add a mesh line. So what we will do actually is to add a line here between 0 and 4. Then we will add some points in this line. Then we will create a line made by sets of this line. So we will allocate a line on each point of another line. This will create a plane, so a grid. And then we will create a third line that we will duplicate this plane and the other axis. So let's do it in this way. First we will create one mesh line of 10, and we will maybe do it 0.2 or 0.4. so this will be the step of the points that we will have, and we will start with -2 in x, -2 in y, which will be this axis here. We will start 0 in c, so we will do 1 point each 0.4 or 40 centimeters. Just remind that this is 4 meters height, so this will cover the 4 meters. Then what we need to do is instances on points. Instances on points. Something I have noticed in Blender 5.0, and this is what just happened, that sometimes when I have one node selected and I add another node, what Blender does is replace the previous node. This didn't happen to me in Blender 3 or 4. Let me know in the comments if it happens also to you. Maybe this is one new feature on Blender 5 that we don't know, but it's quite annoying for me, I would say. So the points will be the mesh. We will set the points here. So our points will be those points that we have defined in this edge, and what we'll have as instances, as I mentioned, will be another line. So we will put a line, a new line in the other direction, in Y direction for example, in each point. So again we will write mesh line, and this time we see, okay, here the start location, we lost it when we put it like this, and the offset will be in Z, so we will be like this. Now the start location will be 0, 0, because we will link it to the point location, and we will not propagate it in Z, but we will propagate it in the Y direction. Oh, sorry, we will put 0.2, and now we will do it for a third time. This will be our starting point. We will add some instances of points here, and here we will add a mesh line. This time we will just consider 0 here, we will add 0.2 in the Z direction, and that's all that we have. Let's connect now, we will see what happens. I think we said we wanted to add 0.4 here, that's why it's not covering everything. So let's put 0.4. I think I did it wrong the first time. And we will have this set of points. Something is still not working properly. We see only the half of the points, and we see also that they are not getting properly oriented as we wanted. This is because we haven't done one step, which will be realize instances. And now we see how our nice vector field is represented here in this case. So we don't need to define many domain that we have. We don't see many of those here because they are 0, and we have set the scale to 0 in our the scaling node of Blender for the glyphs. So we don't need this anymore. We will just remove these grids, and we will keep this as our set of glyphs. Something we can do is that we will know that this is 4 meters, so we will maybe add some value that will increase or decrease the number of glyphs in this case, and this will tell us how many arrows we want in each direction. As we want all the same value, we will connect it to the same here count, and here we will put the count. And what we need to do is now just make computation so that all number of arrows are inside the domain. So this will be 4 divided by the number of arrows, and this will be our step on each direction. So math node, and we will just say divide. So the value we will divide over this. So this value here, which is the scale, we will divide it by the input, which will be the number of arrows, and this will be the step that we will add here. So what we should do is now add a combine XYZ. Here we will set it, but we will connect it to the Z. We will duplicate this one. Of course, here we should put 4. We will duplicate this, Shift Z, duplicate duplicate this one. We will connect it to the Y and connect it here, and we will duplicate it, connect it to the X and connect it here. Now we have everything. Let's see how it looks when we vary this number of arrows. So we have our group node. The group node is this one here. We will rename it. We will name it as grid. Let's put some fancy 3D grid. And we have here the count of arrows that we want. Let's put, for example, 20. Very nice. Cool. Cool. So we have connected both of the Gaussians. We will remove one. We don't need it for this tutorial. We just cut here. Right. And we will make this one a little bit smaller. So now we have our source of density. Now we will create a more sophisticated scalar field by creating a donut of density, not only one sphere but also one donut, and we will use it to propagate some ink or some dye inside the torus with the influence of this sphere. This is what we will do for the tutorial today. So we will remove just this Gaussian. We will not need it anymore. We will build our torus, so in companion with this Gaussian. So to build the torus, let us just remind that the equation that we will use is this one that I'm showing here, where we will have a u coordinate and a v coordinate. The u is the one that is located along the plane of the maximum radius of the torus of this donut, and v will be the coordinate which is for the small radius or the minor radius of the torus. So what we will need to compute first is the difference or the position between the center of the torus and any position of the domain. So let's do it. Let's start with the position node. We will build it. We will need some space, so we will build it from here. Just grab it here, and we will build it independently here. Then we will make it a single group node, so that we don't have to care about it anymore. So we have the position. We just need to subtract position by the center, so we will define just a vector input, and this vector input will be the center. Let's keep the center in the center of the coordinates. Maybe we'll just move it 2 meters above because of our cubic center actually in that place. And we will add a vector math, which will be subtract. Let's subtract this. Then our vector p will be this one minus this one. Now what we need to do is compute the component perpendicular to the axis, so the radius perpendicular to the axis. For this, then we will just need to compute. We will need to define a normal vector, which will be the vector normal to the axis of the torus. If this is the donut, this will be perpendicular to the axis of the main radius. So just add an input constant vector. This we can rename. We can call normal vector of torus. Now we will compute the dot product between these two. So to compute the projection of this vector into the axis of the torus. So we will compute the dot vector, the dot product between these two. This axis we will keep it as y. So we will orient our torus in this direction. So here, positive y. And then what we need to do is scale this by the normal vector. Scale. So we will have the direction of this vector multiplied by the component of the radius projected on the x-axis of the normal vector, in which in this case this is the y-axis. Now we will add a second subtract, and we will subtract this new vector that we have minus the position vector that we have previously, and we will compute the length of this new vector. And this will be the distance of each point, of any point, to the torus plane. Now we will just compute the u coordinate, and the u coordinate will be just the difference between this distance and the radius of the torus. So let's define the main radius. Input as value, and we will put, for example, 1 here. We do the difference, so subtract, and now we have the u coordinate. For the v coordinate, we have it already. This will be the dot product, so this will be the coordinate. So the u coordinate is the coordinate along the plane, so we have it already by doing this difference. And the v coordinate we have computed already as the dot product of the p position vector and the normal, so we will use it from here. What we should do now is to define the sigma. In this case, we will keep the same sigma of the Gaussian. We'll just rename this. We will call it R. Sorry. It will be actually P dot N, and this is R. Let's add another input. So we call this R to be the radius of the torus. This is sigma, the deviation, or the width of this density. And now we will just divide this u over sigma and v over sigma. V we can compute it from here, p dot n. So we'll just add divide, and we will connect the sigma, the same sigma here. We will assume that this is isotropic. Ideally we should use sigma times 2 or sigma squares times 2, but we will observe this constant here in the sigma itself. Now we have this, we will just add them, just add those two values. Sorry, we need first to compute the power. So we compute the division square, and we do the same for the u over sigma square power. Exponent is 2. Now we can add them following our torus equation, and we multiply it by -1. And now we compute the exponent. This will be then our equation of the torus. We will maybe keep the inputs outside, which will be again the center of the torus, the normal vector, the position. The position we can keep inside, we don't need to change it. We will just keep this outside. I'm just doing this because we will create a node group from here. Just Ctrl G, and so we keep vector and 2 values as input, and our output we will connect it here, which is the density of this torus. Now we just rename as torus, and it's nice because we can control the radius and we can control the sigma and the center. Maybe we could have also keep the normal, but yeah, we can live with that. For now, I will connect this here and we will see the nice torus. I have also shifted the source here to 2 in Z, 2 in Y, 0 in X with this sigma, and we have now this torus. If we add these two, we will see the density there. I have also, out of cameras, I have edited a bit the proportion of these arrows by changing here the map range between 1.25, we were not considering the 0, and we will map here from 0 to 1 so that we will have a bigger range of sizes. So now we can see that the smaller arrows are small with respect to the bigger ones. This is give us more idea of the increment of the density. Additionally, I have also changed the radius of the curved circle inside the arrows group to 0.02, the radius to 0.05, and depth to 0.4. This is what is giving these nice arrows that we have now, a bit more proportional, and they are not so elongated as they were before. This with respect to the previous tutorial that we have. Now we have everything that we wanted. We have the torus, we have a nice defined scalar field and the vector field that represents its gradient. What we want to do now is to create a drop of ink or a drop of nutrient or a drop of sediment that will propagate in this velocity field. So it's like you are putting one ship and you let it just navigate along a river, or you are just adding some particles that will just propagate in a fluid, for example. We will in this tutorial we will just compute the advection part. We will not compute the diffusion. The diffusion can be set to another tutorial, but we will show in this tutorial how easy will be just computing the advection in Blender 5.0. So let's start by defining which will be this new ink drop. We will just create one sphere based on our original geometry, and then we will compute the simulation group nodes, and we will advect this as if the velocity, so we will add to each point of this drop, we will add the velocity that we'll have inside this field. We will we'll see how this is computed. So for that, let's start by adding a position node. and which will be the coordinates inside our domain, and we will add input vector. As always, this will be our center, the center of this drop. We will just keep it as 0, 0, 2, which is the center of our domain. So here where this empty is located, we will just make a subtraction of these two. Subtract. And we will compute the length. So this will be the distance between any point of our domain and the center, in this case, this vector, right? We will add compare node less than, and this will mean that we will choose all values that are inside certain radius. So we will add this value, call it radius. This will be the radius of this drop that we have. So let's put 0.5, and that's it. So the result will be all values that are at a distance less than 0.5 or square root of 0.5 from the point that we define here. So this will be like the definition of a sphere. We will add it like a droplet of nutrient or a droplet of the material that will be advected inside the field. So what we have to do now is the same that we did for the Gaussian and for the density. We will just add a field to the grid, and this field will be our ink. So let's do it. We just say we will add a node called field to grid. We will connect our density grid, and the result will be the values that we choose. Next, same as we did here, we will just do grid to mesh. Again, all these values or these nodes are new nodes in Blender 5. So all these computations we are doing so easily is because of the creation of these new nodes. And then we can connect these. Now we have a mesh defined from this density grid based on this spherical outline, and we will just link it to our output node so that we will be able to visualize it. So just add a joint node, joint geometry. We'll link it here, and we will just paste this here. Let's see how this looks. Good. Now we have this ball, this sphere that is defined based on the voxels that we have defined initially here on the mesh to density grid. So this voxel size will affect all these small cubes that we see here. We can refine it, we can make it smaller, so to make it look a bit softer or smoother, but we don't need to do it because this will be in any case evolve to a different shape in future. So not to overload our simulation, we can keep it on this size. What we can do instead is just set shade smooth. This will make it a bit smoother, even though maybe just a bit. And that's all. We have now defined our scalar field with the vector computation, the gradients, and we have a droplet here that we want to advect inside this new field. This is getting quite interesting. Now let's just include the simulation node. So let's grab this here, and we will add the simulation nodes here inside these two. Just maybe grab it here so that we have some space. So now let's shift A and just add the simulation group node, and we will link it we will put it here, even though the linkage will be some way particular. The geometry that we will enter here is our input geometry. And we will just cut this part here with control right click. The topology, we will put it as an input, and then automatically in Blender we will have same output. So this is the quantity or the element that we will affect frame by frame inside the simulation. This we connect here to the grid, and so far we haven't done anything. We will still see our grid here. We will still see we will just connect this here, and we will see still same the same object that we enter here. We are not doing anything, we're just passing everything as same. Let's disconnect this now, and we can add our wonderful Blender node, which is just called Advect Grid. It's incredible how easy it is to just evolve some quantities in a field of velocities just with this Advect Grid. This has a lot of potential. We will just briefly explore what can be done in this tutorial, but the possibilities are countless. And it's very easy. It is quite trivial. What we have to do is delta time. We can just connect it here on timestamp. We can scale it, but we can keep it like as it is. The result, which is our grid, we will connect it to the grid, and here the output, we will connect it here to the result. We don't need to connect the geometry because we are just setting the, or we are just using the grid, and then we are converting the grid to a mesh, which is the one that we are connected here. So we don't need to do anything with the node or the part of the geometry. Finally, what we should define is which will be this velocity that we will use to compute the advection. This is quite obvious. We just need to use the same gradient field that we compute for all the arrows in the previous tutorial. What we want to do though is just normalize it and then scale it. This will give us some control on the influence that this velocity will have on the quantity that we are advecting. Since the speed is actually minus the gradient, we will just multiply this by -1, and we can scale it. We can make it minus 0.5. What this will represent is that the speed at which we will advect this quantity is less if we is the half if we put 0.5. So the evolution of this droplet will be slower than if we just put 0.1. So it will fly faster if we put 1 here. So let's connect here the velocity, and that's all. We have everything already in place to advect this droplet inside this scalar field. Let's hit the play of the simulation and we can see how it looks. This looks already very nice. I want just to increase maybe the size of this source and decrease the radius of the torus. Additionally, what we have here is the vector field is showing the gradient, but maybe it will be better to show directly the speed. This will be quite easy. I will just multiply here the alignment to -1. So we'll just have the same scaling. And just multiply by -1. So what we are showing now are the arrows that the quantity will follow. So if we see this is going outside, this is why this is moving in this direction, and also this is pushing this quantity in this way. That's why these borders are generated like this. Let's just increase the size of this part. Maybe the Gaussian we can add it to 0.8. .6. We will also then maybe reduce the size of this. We will keep it like this, but we will make this one an attractor. So instead of pushing out the quantity, we wanted to pull it to its interior. So it is easy. We just instead of adding here the two densities, we will subtract, and you will see that these arrows now change direction. So this means that quantities will be pulled inside this torus, and we don't see anymore the density because the volume cube is not able to show negative densities. In order to fix that, we will make some dirty trick here. We'll just add another node and put an add. This is not quite elegant because we will not show the actual difference between this density and this, because the one is negative, let's say, or this we cannot call it any more density. We can call it just one scalar quantity that is negative, and we can but just for the example, I will just add this here and add it here. We can say that we are showing the magnitude, or the absolute value of this scalar. We have it, but we will not tell anyone that for this example we are doing this bad trick. Okay, now let's play again the simulation. We will see how this attractor will work. And finally, something that we can do is just probably reduce a bit or increase the voxel size so that the simulation is a bit faster. Let's put 0.05. This will look something like this. I have also just changed to cycles, and we can modify the quantities of the torus. I have set 1.4, sigma 0.2, and let's put 0.25. This will look like this. And I have just removed the density field to make the visualization a bit faster, but we can still see it here. Let's add some material to this ink. To do that, just simply we can do as always, we just add set material node. And we will define this material then. Sorry, not here. This will be very small. Let's go to the layout. And here we can define this ink material. That will be just a simple material. Some metallic properties. Low roughness, I have called it ink, and we just need to assign it to our set material. So here we will just select ink, and this will be material we have chosen. It's nice because we can see the reflections of the arrows on top of it. And that's it. Let's play the simulation. Now it will be running faster because we have reduced the size of the voxel. You can see that it's much faster. And this evolves in this way, creating kind of a fungus. Hollow fungus, because this is pushing in this direction and then this is like pulling in the shape of the torus. This is what we wanted to achieve. Let's just let it finish. You can see that this has become hollow. So cool. We can play a bit with the size of the torus, with the intensity, with the speed, with all parameters that we have. And I think, yeah, we can just keep it 1.4 or maybe 1.0.2 and 1.40, something like this. We see how this is affecting our geometry in this. And that's it. This is our result. We have very easily advect some quantities in the scalar and vector field. We have been able to fix the arrow size and shape. We have created a more interesting scalar field. I hope you like this tutorial, and don't forget to see the first part here. I will continue making some exploration on the new geometry nodes from Blender 5.0, so subscribe to the channel so you will not miss it.